Dear students, in this today's lecture session, I am going to explain you about basic concept of infrared spectroscopy. So before handling the FTIR instrument, one should have some knowledge regarding the principle and instrumentation of FTIR as well as sample handling while using the FTIR. So infrared spectroscopy is a qualitative technique through which one can find out different functional group present in the organic compound. By virtue of the spectra, one can predict the structure of organic compound. So spectroscopy is the branch of science that deals with the interaction of electromagnetic radiation with organic compounds. So electromagnetic radiation, it ranges from the shorter wavelength towards the longer wavelength. So the shortest wavelength is known as a gamma rays and the longest wavelength is a radio frequency wave. So based on the wavelength, the shorter wavelength has a higher energy as compared to the longer wavelength. So longer wavelength, lower frequency, shorter wavelength, higher frequency. So based on the wavelength, the organic compound will have a different kind of changes observed. In case of the X-ray, there is a ionization, UV visible, it will produces a changes in the electronic level. So electronic transitions are recorded in UV visible. Our interest of spectroscopy of today's, that is a infrared, so it causes a molecular vibration, that is a stretching and bending in chemical bonds. Microwave causes the rotational motion and radio frequency in terms will causes a nuclear spin transitions. Infrared spectroscopy provides the sufficient information regarding the structure of a compound, and this technique is mainly used for the qualitative purpose. It gives you the idea about the functional group present in a compound. As for the IR spectra is concerned, IR spectra consist of wealth of information, that is a huge number of peaks are observed as compared to UV visible. Because in IR there is no electronic transition, the only transition we are observing is a vibrational changes. So infrared radiation, it is in between the visible and microwave of electromagnetic spectrum. The IR radiations are further categorized into three regions: near IR, that is 14,290 to 4,000 reciprocal centimeter; mid IR is 4,000 to 400 reciprocal centimeter; and far IR is 400 to 200 reciprocal centimeter. Our area of interest is a mid IR, that is a 4,000 to 400 reciprocal centimeter. Practically, we also say mid IR is 4,000 to 670 reciprocal centimeter, and in terms of microns, it is a 2.5 to 15 microns. Each and every compounds will not absorb the infrared radiation. For example, if we take a compound like oxygen, nitrogen, hydrogen, where the net dipole change is 0, that compounds will not absorb the IR. So to absorb the IR, the molecule must have net change in the dipole moment. So there should be a generation of delta plus and delta minus in the atoms between the chemical bonds. Then only that chemical bonds can absorb the IR. So there should be slightly positive or negative, that is atom with different electronegativity. So the alternating electric field present in the infrared radiation will causes a fluctuation in the dipole moment. So that in terms will causes the net increase or decrease in separation. For example, the natural frequency of vibration of hydrochloric acid is 2890 reciprocal centimeter. When the IR source having a 2890 strike the HCl, it will absorb this 2890 reciprocal centimeter radiation from the electromagnetic radiation source, and in terms it will causes change in stretching of a compound. So the chemical bonds present between atoms, this is one atom, this is another atom, the chemical bonds are in the form of the spring. So and due to the change in the electronegativity, there is a generation of a dipole moment. So when the IR strike this, it will absorb the radiation. Due to that, this bond length will either stretch or it will compress. So there is a change in the net force of the chemical bond. So there will be a either stretching of the bond or compressing of the bond. So that is recorded by the IR instrument. In infrared spectroscopy, we study molecular vibrations. Molecular vibrations are vibrational changes. They are divided into two classes. The first is known as a stretching, and second is known as a bending or deformation. So stretching is change in bond length, that is a change in the interatomic distance between two atoms, and stretching is further categorized into symmetrical stretching and asymmetrical stretching. In symmetrical stretching, if we are considering the two chemical bonds, both bond length is either increasing or both bond length is either decreasing, then it is known as a symmetrical stretching. And in asymmetrical stretching, one bond length is decreasing and another bond length is increasing, then it is known as a asymmetrical stretching. As for the bending or deformation is concerned, it is related to the change in the bond angles. So bending or deformations are of two types. One is in plane bending and another one is out of plane bending. So in plane bending is, it has a symmetry of plane of symmetry is there. First categories of in plane bending is a rocking, where the bond angle will just rotate or swing, however it is constant, while in scissoring the bond angle decreases. While in out of plane bending, one is on the same side of the plane, so we are mentioned here near or positive, which is known as a wedging, and in another twisting, one is above the plane and other is below the plane. So we have mentioned near plus and far minus, then it is known as a twisting. So stretching, we have a symmetrical and asymmetrical. Bending or deformation, we have a in plane bending, that is a rocking and scissoring, and out of plane bending, they are wedging and twisting. In infrared spectrum, the frequency is measured in terms of wave number, that is represented by the nu bar. So this is the symbol nu bar for the wave number, and wave number is just defined as the number of wavelength per centimeter in vacuum. Nu bar equal to 1 upon wavelength, and wavelength is centimeter, so nu bar is, the unit of the nu bar is a reciprocal centimeter. And the band intensities are measured in terms of the transmittance T, that is a percentage transmittance. So transmittance is defined as radiant power transmitted by sample upon radiant power incident to sample. So absorbance equal to log to the power 10 1 upon T. And the peak intensities, they are measured in semi-quantitative terms, like if the intensity of peak is strong, it is denoted by S. If it is medium, it is denoted by M, and if it is weak, it is denoted by W. This figure is the representation of the infrared spectrum. So in infrared spectrum, in the y-axis, we have a percentage transmittance. It ranges from the 10 to 100%, and in the x-axis, we take a wave number that is ranging from 4000 to 400 reciprocal centimeter. So here there is an example of one of the spectra of compound aniline. So in aniline we have a NH2 functionality. So NH2 functional group, it has a two type of stretching, that is a symmetrical and asymmetrical. Two peaks you can see in the spectra. So this is for the NH2 stretching. Then we have a NH bending around 1650. This is the NH bending peak, and rest of the peak like this 3000 around is a CH stretching of the aromatics. Then around 800 we have a CH bending of the aromatic CH outer plane bending. So this is how the spectra is represented for the molecule compound aniline. Now I am giving you one example of organic compound acetaldehyde. It has a general formula CS3CHO. So there is a C double bond O. So this is the main functional group, that is a aldehydic functional group. C double bond O is a carbonyl group, and CH is a CH of aldehydic functional group. C double bond OS, this is a aldehydic functional group, and acetaldehyde is a aliphatic aldehyde. Here the chemical bonds I have shown you in the form of the spring. So it indicates that it is not a rigid chemical bond. It can absorb and it behaves like a spring in nature. And here double bond O, one is a solid line and another is a spring, that is our C double bond O. When we take an infrared of acetaldehyde in the FTIR instrument, the carbonyl functional group absorb at 1730. So 1730 reciprocal centimeter is a CO stretching of the aldehyde. Likewise, CH of the aldehyde stretching absorbed at 2720 reciprocal centimeter. Likewise, this methyl group's CH stretching is absorbed at around 2960 to 2870. Likewise, CH bending of methyl group is observed at 1460 to 1365 reciprocal centimeter. This in terms explains that if those absorptions are there in the infrared, then we can say that our molecule is acetaldehyde. Now I am going to explain the region of infrared spectrum. So infrared regions is ranging from around 400 to 4000 reciprocal centimeter. It can be further divided into different regions. For example, if there is a 4000 to 3000 reciprocal centimeter, in this region OH stretching, NH stretching and CH stretching takes place. In 3000 to 2000 reciprocal centimeter, generally in this region, triple bond compounds or the sp hybridized systems absorption is taking place. For example, C triple bond C like in alkyne, or C triple bond N that is in a nitriles. This triple bond compound, it absorbs in between 2000 to 3000 reciprocal centimeter, and in 2000 to 1500 reciprocal centimeter we have a double bond system. It may be a C double bond N or C double bond C like in alkene C double bond C, or aromatic ring C double bond C, or a carbonyl C double bond O absorption. It is taking place in 1500 to 2000 reciprocal centimeter. So this is very important region, because our one of the most important organic compounds are carbonyl compounds. So aldehyde, ketone, amide, ester, acids, all these compounds C double bond O group, it absorbs in 1500 to 2000 reciprocal centimeter. And the carbonyl group, as carbon and oxygen has different electronegativity, we will get a sharp peak, and it can be easily visible, and we can separate it out from the other peaks. Then 1500 to 1000 reciprocal centimeter, we have generally single bond absorption like CO, CF, CCl, and different deformation. It takes place in 1500 to 1000 reciprocal centimeter. As it moves toward the 4000, there is a increase in the energy as well as increase in the frequency of absorption. So as it moves from 400 to 4000 towards this direction, that is towards the left hand side, there is increase in energy as well as increasing frequency. This is the another pictorial representation of infrared range, where we have categorized the region into two types. In these regions, we call it as a fingerprint region. It ranges from 600 to 1400 reciprocal centimeter, or we can say that below 1400 reciprocal centimeter, it is a fingerprint regions. And in this region, generally single bond C single bond C, C single bond O, and CN stretching is taking place, and certain deformation vibrations are taking place. It is just like a fingerprint of the human, so that it exactly give you the idea about the absorption of corresponding bonds. Likewise, 1600 to around 3500, this is known as a functional group regions, and functional group regions is further categorized into 1600 to 1800 for the double bond C double bond C, C double bond O, C double bond N, 2000 to 2500 triple bond C triple bond C, C triple bond N, and from around 2800 to 3500 we have a NH stretching, OH stretching, and CH stretching. One thing we have to remember that no two molecule will give exactly the same infrared spectrum except the enantiomers, and complex vibration that is observed between 600 to 1400 reciprocal centimeter, it is called as a fingerprint region. Now moving to the IR instrumentation. So in IR we have a dispersive infrared spectrometer, that is a double beam IR spectrophotometer, or it is also known as a conventional infrared spectrophotometer. So in double beam infrared spectrophotometer, it is somewhat similar to the double beam UV spectrophotometer. Just difference is that the source of electromagnetic radiation will be the difference. So here in this figure you can see the glowing wire source. So this might be a incandescent lamp that is producing the mid IR region of here 4000 to 400 reciprocal centimeter. Then this radiation will pass into the monochromator, and the light sources will deflected into two directions. From this mirror, one light will move to the reference cell and another light will move to the sample cell compartment, and when it combines it will remove the reference cell and it will give you just the absorption of your compound, and it will reach to the detector, and finally you will get a spectra like this. So this is the dispersive infrared spectrophotometer, that is double beam IR spectrophotometer. Whenever we use a term dispersive infrared spectrometer, in that instrument there will be a monochromators like prism or gratings, that is converting the polychromatic light to the monochromatic light. And as double beam word is there, you have to remember that there are two compartments. One is for the reference cell, that is for the blank, and one is for the sample cell where we are placing our sample through for which we need a IR spectra. Recent days, we generally preferred FTIR instrument, which is known as a Fourier Transform Infrared instrument. In Fourier Transform Infrared instrument, there is one part of the instrument which we call as a Michelson interferometer. So this Michelson interferometer has a beam splitter, and the radiation from the IR source, it is deflected into fixed mirror and moving mirror. It recombines and this radiation will reach the sample. There is an absorption and it will reach the detector. Beside that, we have a laser beam. This helium neon laser beam, it is used for the spectral calibrations. So this is a layout of the FTIR instrument. So instrumental diagram is shown here. In this part is optical part where we have a different mirror and the interferogram, Michelson interferogram. This is for the sample compartment where either we can use a KBR unit or the ATR unit, and this is a detector. So this is the instrumental part, and the spectra I have already mentioned you. In y-axis we take a percentage transmissions, and in x-axis we will take a wave number, and this is how the spectra looks like. So the question arises, how does an FTIR spectrometer work? The basic principle of all FTIR spectrophotometer is based on the Michelson interferometer. So this is the part of the Michelson interferometer. There is a source of radiation, that is an infrared source through which IR radiation is coming out. Then there is a beam splitter. It is made up of potassium bromide, potassium chloride or zinc selenide and half silvered mirror, so that the light will move to the stationary mirror and the movable mirror. So the distance of the movable mirror changes and the accuracy of instrument lies on this movement of this mirror. Then when this reflected backlight comes and combines in this beam splitter part, it is known as an interferogram. It is encoded with the all signal of the infrared. Then it will reach to the sample, it will absorb, and it is detected. Based on the movement of the movable mirror, we have a two type of interference. One is known as a constructive interference and another is known as a destructive interference. So when the source radiation comes, it will reach to the stationary mirror, it will reflect back, and there is a movable mirror. When this movable mirror and stationary mirror both have a same length, for example we say both have a lambda by 2 and lambda by 2 length, so it is equal. So when it combines, it becomes a lambda. So this is a constructive interference. And when the integral values ratio it comes, then it will it is referred as a destructive interference. So lambda by 2, 3 lambda by 2, these are known as a destructive interference. Lambda, 2 lambda, 3 lambda, 4 lambda, like that, then it is known as a constructive interference. When it combines in this interferogram, it has both constructive and destructive interference, and they are coded with all regions of the FTIR. It will reach to the sample, it will absorb, and it is detected. So another important aspect is a sample handling techniques in infrared. So in infrared, we can handle both the solid sample, liquid sample, and the gaseous sample. So all type of sample can be analyzed in the IR. However, we do not prefer the solution form as there is a change in the intermolecular forces. However, if the compound has a polymorphic variation, that is different crystals are giving the different kind of spectra, in such cases, polymorphic cases, we can analyze in the solution form. For the solid sample, we have three different techniques like potassium bromide discs or KBR discs, Mulls technique, and deposited film. So solid sample can be analyzed either of these three techniques, either KBR discs, Mulls, and the deposited film. In KBR discs or pellets, what we are going to do is we will take a sample around 0.1 to 2% by weight, and taking 100 times its weight of powder KBR, we are grinding together and compressing it to give a wafer disc or pellet. And whenever we are grinding the KBR, we should use a KBR lamp to avoid the condensation of the atmospheric moisture, because if water is present, there will be a broad absorption at 3500 to 3000. So there is an interference of functionality absorption like OH, NH, or CH. So for the compression, we should have a high pressure system should be there. We are using special die and different hydraulic press that can produce a 10 tons of the load. Generally, the disc should be handled by the edges, and it should have a 13 millimeter in diameter and 0.3 mm in thickness. Another analysis of the solid sample is by using of Mulls or Mulling agent. So we are grinding the sample with a drop of oil, which is known as a mull, and that is squeezed between the transparent windows, and then that windows is placed in the IR instrument. For that, the mulling agent should be IR transparent. If we are using a liquid paraffin or nozzle, that is a high boiling petroleum oil, as a mulling agent, it generally absorbs at 2915, 1462, 1376 and 719 reciprocal centimeter. Same absorption is there for the CH stretching and CH deformation. So it is difficult to study CH stretching and CH deformation if we are using a liquid paraffin and nozzle as a mulling agent. However, we can use other mulling agent like hexachlorobutadiene, which absorbs at 1630, 1510, 1200 and 1140 reciprocal centimeters, and we have a chlorofluorocarbon oils, perfluorokerosene, chlorofluorogreases, fluorotubes. This can be used as a mulling agent. Another technique for solid sample is by making a solid films. For that, we deposit the sample with volatile solvent on NaCl plate and allows the volatile solvent to evaporate, so that there is a formation of the solid films, and that can be kept in the instrument and we analyze, it is generally preferred for polymer and waxy substances. And for the liquid sample, we have a thin film of liquid can be formed in the IR transparent windows, and we can analyze the liquid sample, and once the analysis is over, it should be washed with a suitable solvent like choline or carbon dichloride. For spectra down to 250 reciprocal centimeter, cesium iodide flats are preferred. If sample contains water, then calcium fluoride flats are used. For the analysis of the solutions, we have to dissolve our solutions into carbon tetrachloride, that is a CCl4, or carbon disulfide CS2, or chloroform, that is CSCl3, and the spectra of solution is recorded. So 1 to 5% solution cell containing transparent windows and spacer between them should have a sufficient thickness. The spacer is made up of lead or polytetrafluoroethylene. And for the analysis of the gases sample, so there are available gas cells are available, and it is used for the analysis of different pollutant gases. Sample handling in the infrared is one of the cumbersome process, and it is a time taking as we have to prepare caviar pellets or the moules. So nowadays we widely use ATR crystals. So ATR crystal or the ATR plates, in that we can directly introduce the sample and we can carry out the spectral analysis. So the attenuated total reflectance ATR principle is based on the total internal reflectance. So there is a zinc selenide or germanium type of crystal is there. It is shown in this diagram. When the light radiation strike here, there are two medium. This germanium has a medium one. It has a high refractive index, and when the light goes in medium 2 or air, it will bend away. As you increase the internal angle, incidence angle, at a certain position, the boundary angle becomes a 90 degree. In that condition, the incidence angle inside it is known as a critical angle. When further we increase the critical angle, there is a total internal reflectance. When there is a total internal reflectance, still there are certain weak waves that is passing through the boundary, which is known as an evanescent wave. This evanescent wave have a mid-IR regions radiation. It causes stretching and bending, and after absorption it will reach to the detector. So because here source of IR radiation through Michelson interferometer, it is striking here, and the mirrors are placed in such a manner that it is giving a total internal reflectance, and there is generation of an evanescent wave. As the evanescent wave is a weak wave, we should have at least 25 to 50 total internal reflectance. So this multiple internal reflectance in terms causes strong evanescent wave and sample absorption, and it will reach to the detector. So this phenomena is also known as a frustrated total internal reflectance. To sum up, in this technique, total internal reflectance creates the evanescent wave in boundary, and it causes a sample to absorb the mid-IR regions, causes stretching bending, and it will reach to the detector. So in this figure, this yellow color, it is a ATR element, and this is a sample, and from IR source there is incoming radiation. It may be from the Michelson interferometer, it strike, there are lots of internal reflectance taking place, evanescent wave will causes the absorption of a compound, and this existing light will reach the detector. So different IR fused materials are calcium fluoride, barium fluoride, zinc selenide, and these are the different absorption range in the reciprocal centimeter. This is the chart for common ATR crystal material. So these are in this column. There is a material like germanium, silicon, AMTIR, zinc selenide, and diamond. So this is the mid IR range. So for example, zinc selenide, which is commonly used, it has the range of 15,000 to 650 reciprocal centimeter. This is the refractive index values for the ATR materials, and this is a depth of penetrations at 45 degrees Celsius and 1000 reciprocal centimeter. This is the depth of penetration. So germanium is preferred for the sample with strong absorption and dark polymers. Silicon for the is resistance to basic solution, and zinc selenide is used in the general purpose, and diamond is preferred mainly for all kind of compounds from caustic to the hard sample. This is the ATR units where there is a ATR plates. This is for the solid sample, and if there is a groove, it is for the liquid sample. So in this plate we are placing the sample, and this is attached to this ATR units, and this is installed in the instrument, and we analyze the compound. So this is how the ATR materials or ATR units looks like. So if solid, so there is a solid surface. If liquid, there is a groove. Inside this groove we can fill the liquid, then this is attached in the instrument through this attachment unit. Thank you for patiently listening the lecture. This is the lecture meant for the FTIR practicals. In practical session, I will demonstrate you how to prepare a KBR pellets and analyze in a FTIR instrument. Once again, thank you.